Hi guys, welcome to section C. We're going to keep talking about electricity. So I told you we were going to get back to this idea of circuits, okay? So if you remember from first section, we talked about current and the fact that this electric current has to flow through a loop, okay? What we're talking about here is something that looks like that, okay? It needs to be a complete loop. An open circuit is an incomplete loop which prevents flow, and a closed circuit is complete so the current can flow. Okay, so if you have a switch here, and sometimes, maybe my pen, sometimes these circuits are actually going to be drawn with symbols. Okay, so you're going to see symbols like this, and then here's the wire, and then it goes like that. That's the light bulb, and then there's the switch. Okay, we'll talk about those a little bit more. This would be an open circuit because that switch was open, so the electricity can't flow, the current can't flow. If the switch is closed, put into the on position, now it's an open circuit. Now it's a closed circuit, and so now the loop is complete, and so the electricity will flow through a resistor right there. A lot of times it's a light bulb. That's at least what we'll be doing in class. We'll be building with light bulbs, and then it goes back. Okay, and the battery is the voltage source there on the side. Sometimes you have a short circuit. Okay, so if this current takes an unintended path or it kind of breaks off and finds another circuit, it can be very hazardous. Okay, that's what the definition of a short circuit is. We're going to talk at the end of this lesson about some different safety features that are built in to kind of protect us for when things like that happen. Okay, so this is what's known as a series circuit. Okay, there's only one path for the current. So there's our battery source, there's our symbol. We've got three resistors. Okay, these can be light bulbs, these can be different, devices that are going to use the electricity, the current. The reason I like to think of them as light bulbs is because the way a light bulb works, an old-fashioned light bulb that Thomas Edison designed. There's my little light bulb. Okay, there's literally a wire that goes through the middle there and attaches. Okay, so when the current flows into that wire up this way, there's resistance through that wire. It's different wires up the top, and then it goes down. There's so much resistance, it almost makes like friction, okay? And it actually heats that wire up until it glows, and that's where the light of a light bulb comes from, okay? So when I see this little squiggly line on these circuits, I think of that little squiggly wire inside of an old-fashioned light bulb. That's the kind of light bulbs we'll use in the classroom, and so you'll just kind of know that whatever is taking the current, whatever is using the current is resisting the current, and that's where that energy is kind of going off and being used. So a series circuit has those resistors in one loop, one pathway, okay? So the current has to go through resistor 1 in order to get to resistor 2, and has to go resistor 2 to get to resistor 3, and then to go back to the battery, okay? Every bulb you add to this is adding resistance, and so the bulbs will get dimmer as they go, okay? If one of the bulbs burns out, or if you remove one of these resistors, you've now opened up that circuit. It's now an incomplete circuit, and all the rest will go out because the electricity cannot complete that loop, okay? So now we have this thing that's called parallel circuits. And these are a little different, okay? You can still see here's our battery source, here's our three light bulbs, okay? But now we've got alternate paths, okay? So electricity can go here or it can go there, okay? Because there's additional paths, there's not as much resistance. Not all of the electricity is going to come through that light bulb right there. Some of it is going to go off in that direction, okay? Which means in these parallel circuits, the light bulbs are all brighter. They don't dim down the other ones, okay? And let's say I take this light bulb out, or this light bulb burns out and the wire is broken and it's now an incomplete loop. Okay, well, I can still have a complete loop there, and I can still have a complete loop there. So the other two bulbs will not go out. Okay, the current can find an alternate path with these parallel circuits. Okay, there is a downfall though. You could overload these. Our houses are mostly set up with parallel circuits. And we're going to talk about circuit breakers in just a minute. And so if you plug too many things in on the same circuit, it can actually cause it to like overheat, and it could cause a problem. So there's protection for that. We'll talk about that at the end. All right, we've got another formula here. Got to talk about power. Power earlier in the year was just kind of related to energy and work. Okay, so it's the amount of work done per second. Now we talk about electric power, which is the amount of work done per second in an electrical system. So it's really no different, but we do have unique formulas for that because we're going to be talking about voltage. So one of the variations of this is P for power, that's measured in watts, is equal to V for volts, that's voltage, that's measured in volts, and then I is still current, and that's measured in amps, okay? So volts and amps, voltage and current, those are two things that we've already dealt with Ohm's law. Now we're talking about power. And so we've got this triangle thing again that shows us it depends on which piece we're looking for. If we're looking for power, we just multiply the other two things. We multiply the voltage and the current. If we're looking for current, we're going to divide power by volts. If we're looking for volt, we're going to divide power by current, okay? So if you look in your book on page 462, there's a power question. It says, you and your friend are meeting to watch one of your favorite TV shows. The streaming service draws 2.8 amps, so 2.8 amps, and the electrical system is 120 volts, and it wants to know the power, okay? So we're using this formula right there. So you would multiply the 2.8 times the 120, and you would get 336 watts. Power is measured in watts. Now, typically when we're talking about high electricity or the power usage in your house, it's going to be in kilowatts because that adds up really quickly. And so it's in the thousands of watts. And so it's going to be converted into kilowatts to make that a smaller number, right? So we've got some things that help us keep safe. A fuse is something that melts when too much current goes through it. Once it melts, that stops the flow of the current, okay? And so now the circuit is open and the electricity can't keep going. That's just to shut it down when there's too much current. It's to keep the normal wires from potentially catching on fire because they're getting too hot. So the fuse is a little bit weaker than the wire, and it's just to protect the rest of the circuit, okay? If you look in your houses, somewhere in your house, you've got a circuit box, probably out in your garage or your side yard or your patio. It's usually on an outside wall. And these circuit breakers will automatically switch if a circuit gets too much, if it gets too overloaded, there's too much current passing through, okay? That also opens up the circuit and prevents the flow of electricity. So this happens, I know, in the summer a lot when like the air conditioner's on and the TV's on or whatever, and all of a sudden some of the power in your house goes out, not all of it. So whatever things are on the same current will all turn off. Then you have to go and you have to figure out which switch it was, and you just turn it back on. And things will start working again. But you might not be able to vacuum and use the air conditioner and the TV and blow dryer all at the same time, okay? Another thing is grounding. So if you notice, most things that we plug in have 3 prongs, okay? There's the 2 main prongs up there. That's what's actually, connecting the loop of electricity. And then there's that 3rd prong that goes down the bottom. That's the grounding prong. And what that does is it gives electricity a safe path in case it gets off course, in case there's too much of it or it takes an alternate course. And your houses usually have a ground wire, and that wire literally goes into the ground. And so it gives the extra electricity a place to go safely. If the electricity goes into the ground, it's not going to cause a problem, okay? Some of you might have these fancy outlets too with these buttons in the middle of them. Those are called GFI outlets. That stands for ground fault interrupter. And they're commonly used in kitchens or bathrooms where there's potentially water being exposed to some of these electrical appliances. If you drop your hairdryer into the bathtub, it's no good. So these GFI outlets have a little built-in circuit breaker right inside of them. And so if something happens to short circuit it, to overload it, a switch will flip in the outlet and interrupt the circuit, okay? And then you just have to push that button to kind of reset it. Instead of going all the way out to the circuit breaker, you just deal with the button right there on the outlet, and that helps. That's it. See you guys later.